Good afternoon. Section 5.5, the substitution rule. So this is the simplest rule of integration that allows you to take an integral that's not in the table and somehow convert it to something that is in the table. And we'll start from an example like this. Cosine of x squared plus 5, 2x dx. Okay, so this integral is an indefinite integral. We have to calculate the antiderivative. Of course, this complicated function is not in the table, but we can do the following thing. Let us take the argument of the cosine and call it u. Okay. Then let us evaluate du dx. Okay. We have to differentiate it to get 2x. And I also want to write down du as a differential. I solve for du, this simple equation. Okay. So what I see here on the right-hand side is the same pattern as appears in the integral. 2x dx. You can see that it can be expressed very easily in terms of u. It's just du. Okay. So I can rewrite the whole integral like this. Cosine of u. Okay. So this thing is u. Du. This is a huge simplification because now we know what to do. This is an integral that we know. The antiderivative is sine u plus c. Okay, so we start from something very complicated and we reduce it to something very simple by playing with a change of variables. Okay, our old variable was x. I recognize this combination x squared plus 5 as a new variable u. And I identified the rest of it as a differential of u. The last step here is that if this is an indefinite integral, remember it has to be a function of x. So we have to rewrite this answer in terms of x. So we have sine x squared plus 5 plus c. Okay. So how would I ever think of something like this? One way to think about it is like this. You have a function of a function. You can see that this is we have a cosine of a different function. And when we look at this quadratic form, we know that its derivative is 2x. And this is exactly what we see here. So somehow we can recognize a piece of a derivative of this function also present in the integrand. Okay. So with experience, you will recognize this very easily. But for now, let us check that the answer obtained in this way is indeed correct. How can we check that we didn't make a mistake? Exactly. This is an antiderivative. We take a derivative, and the goal is to obtain the integrand, right? So we have to evaluate d dx sine x squared plus 5 plus c. How do we differentiate this? Chain rule, exactly. This is chain rule because we have, a composite function. So the derivative of sine is cosine, and we have to multiply it by d dx of x squared plus 5. And of course, c doesn't give me any contribution to the derivative. So I have cos x squared plus 5 times 2x, which is exactly what appears in this indefinite integral. This tells me that I obtained the right answer. Okay, so questions about this? Let's write down the general rule, which is called the substitution rule. So if u is some function of x is a differentiable function whose range is an interval I, and f is continuous on I, then we can simplify the following integral: f of g of x. Okay, so what I see here under the integral is f of g of x, the composite function, times the first derivative of g dx. If my given integral has this form, then I can simplify it. I can present it completely as an integral in terms of u by using a change of variables. So g of x is u, f of g of x is f of u, and this thing here is nothing but du. Right? And then I can write down the answer. It's f of u, where f prime is f, the antiderivative, which is the same as f of g of x plus c. Okay. So this is a formal way to write down the rule of substitution. Okay. And we will use several examples to illustrate it. Before that, we want to prove it, right? We want to check if it's really true in general. So we have a left-hand side and a right-hand side that have to be equal to each other according to this theorem. How do we check that? We have to differentiate, just like there. We differentiate the antiderivative and make sure that the answer coincides with the integrand. So check. We evaluate df dx, f of g of x. We use the chain rule. So that gives me f of g of x times g prime of x. Okay. So the first part follows from the fact that f is the antiderivative. Okay, so when I differentiate the antiderivative of f, I get f. It's evaluated at g, and this is the second part of the chain rule when I differentiate the internal function. So in brackets, let me write it down actually more. This is df du dx, right? This is f of u g prime of x, and this is f of g of x g prime of x. So this calculation fills in all the steps. Questions? So chain rule is something that we know, and the rule of substitution is the chain rule applied to integration. It's basically the other side of the chain rule. So let's do some examples. The first example is very easy. So let's consider an integral of e to 3x plus 7 dx. So to recognize that the substitution rule should be used, we can see that this is a composite function, an exponent of another function. And the first thing that we try is that we look at the argument of this function, and we say that's my new variable u. Okay. This should be the algorithm of thought that you use to attack such integrals. We try things. Okay. We see that there is a function of a function. Let's make its argument the new variable. And then there's a sequence of steps that should be kind of the same every time. So first we'll write down the definition of the new variable. By the way, if it doesn't work, it doesn't work. So we always try, and we will later see examples where we have to try a few things. But so this one is easy. We write down the definition, right? And then always we write down the derivative. So that's just 3. And finally, we want to solve for dx. So du equals 3 dx, or we can say that dx is du over 3. We want to express everything in this integral in terms of u. So the first part is easy to express in terms of u. It's just e to the u. The second part is dx, and that's why when I differentiated, I solved for dx. So here I have du over 3. Questions? So from this, the equation of differentiation, I can solve for dx, and dx is something that I need to express. Okay. So now, when I get rid of the constant by taking it out of the integral, this is what I need to solve. Can we do that one? Of course. So we have 1/3 e to the u plus c. And the last step we should not forget, the answer should be in terms of the same variable as the given integral. And going back is very easy. You just remember the definition of u, 3x plus 7 plus c. And that's the end of it. Okay, so always write down the definition and then differentiate and see what happens. So the next example is the following integral. X 3 minus 2x squared minus 1/2 dx. Okay. So what do we have here? We have a composite function. You can see that immediately. We have something in brackets to the power of minus 1/2. So perhaps the argument of this function should be taken to be our new variable. And this is what we try. Okay, so we write down u is 3 minus 2x squared. And as the next step, automatically, we differentiate it. So 3 gives me nothing, so I have minus 4x. Now I have to express this whole thing in terms of u. Let me start. So I have u minus 1/2. That's this. And then I have x dx that remains from the original integral. So this has to be expressed in terms of u. And I'm going to do it from this equation. I'm going to multiply it by dx and divide it by minus 4. So first I multiply by dx. And then I divide by minus 4. And you can see that I now expressed x dx in terms of u. Question? Yeah? Questions? Okay, so after getting rid of the constant, I can see that this is easy. Okay. I have u 1/2 over 1/2. And as the final step, I recall what is u. And complete the solution. So what is the reason that the substitution rule worked here? The reason is that my new variable u, when I differentiate it, it gives me x. Okay, so the new variable is quadratic and x. When I differentiate x squared, I get x times some constants. So when I differentiate it, I get x, and I can see x here. So if I go back to the statement of the theorem, I have a function of a function, f of u, and I have the derivative of that function stuck here inside the integral. Okay, so this is a necessary component for this method to work. If I didn't have this x here, I wouldn't be able to do this. Okay. But I'm sure we'll see such examples later. Now we continue with some more integrals. The next one is really easy, but very common. So I do it here. Sine 30x. Okay, we know how to integrate sine x. How to integrate sine 30x? Very easily. We have a sine of a new function 30x. So we say this is u. U is 30x. Du dx is 30. So dx that appears here is du over 30. So I have sine u du over 30. This reduces it to something very simple. Okay. And as the last step, I remember that u is 30x. And that's it. Questions? Question?
Yeah, I was wondering how you're saying like there's a derivative being multiplied by a
Yes.
function.
Yes.
Could you show me again where the derivative is?
Yes. So here, let me bring the. I'll show you exactly what it is. So let us regroup this integral like this: 3 minus 2x squared minus 1/2 x dx. Okay. So the first object here is a function of u, where u is this, and the remainder here, x dx. Includes the function x. The function x is a signature of the derivative of a quadratic function. If you have a quadratic function x squared, its derivative is going to be proportional to x. It's going to be some number, and numbers don't matter when you integrate, some number times x. So here, this includes something like du times a constant. Okay, and that's what I want. This is f of u du. Let me give you another example which will make it more clear. Let's do this one. Sine x cos x dx. Okay? So let me make my new variable to be this whole thing. It's a linear function of sine x. So the two components are the function and the signature of its derivative, which is the derivative times perhaps a constant. Okay? So we can see that if u is sine x, its derivative is also there. Right? We recognize that. And that's somehow this gives me confidence that perhaps it's going to work. So, but we have to go through the steps. So u is sine x, du dx is cos x dx. Well, and I'm sorry, is cos x. So du is cos x dx, and that's exactly what I'm looking for. So this can be written as u times du. Okay? And now it's completely easy. U squared over 2 plus c, which is sine squared x plus c. So I have the confusing bit about this one is that I don't necessarily have a function of a function. I just have sine x. But the next example will show you that very similarly, I can do something else. For instance, we can look at square root of sine x cos x dx. Okay. I use the same substitution. U is sine x. And I've done the differentiation already. So that means that I have square root of u du. So I have a function of a function, square root of sine x, and I have the derivative of this internal function present right here. And this is why the method works. This is why I can rewrite the whole thing in terms of the new variable. So to finish this example, I have sine x 3/2 times 2/3 plus c. Okay? So I have a function of a function and the derivative of the internal function, which could be multiplied by a constant. Okay, so the next example is more complicated. So all of these problems are kind of one step because you just have to follow the rules. You differentiate and you figure out how to express the differential in terms of the new function. Now, this is a two-step problem. So it goes like this. 1 plus x squared, x to the 5 dx. So according to our previous limited experience, we're looking for a function of a function, so this could be a good candidate for the new variable, which I'm going to define here. Now we can calculate du dx, okay? And now let's see. What I told you before is that we have to have this composite function times the derivative of its argument. So the derivative of the argument is proportional to x. And here I don't have x. I have x to the 5. So it's not exactly the same. Okay? So I'm going to try and trick it. So I have 1 plus x squared. And then x to the 5, I'm going to split into two parts. I'm going to say that it's x to the 4 times x dx. So from this equation, when I differentiate this thing, I know that x dx can be easily expressed in terms of u. So let me do what I can. I can express this as square root of u, and I can express this as du over 2. The only thing I don't know what to do with is this. Okay? But let me just continue in the hope that something comes up. Trying to rewrite everything in terms of u. So I have parts of it rewritten in terms of u, and I have x fourth hanging there. Now I go back to the definition of u, and I wonder, can I express x to the 4th in terms of u? Yes, I'm going to use this definition. So this definition allows me to express x squared very easily in terms of u, right? So x squared is u minus 1 from the definition of u. I don't want x squared, though. I want x to the 4th. What should I do? Square it. To get x 4th, I just write down u minus 1 squared. And this is what I have as my next step. U minus 1 squared du. And look, this is already partial success, because I managed to rewrite the integral in terms of x, in terms of an integral, in terms of u. Question? Oh, thank you. Now, Is this any better than what I started with, is the question. I don't want to go in circles. And it is better, okay? Because this is a power, and powers are harmless. I can expand them, okay? So I'm going to write u minus 1 squared as u squared minus 2u plus 1. So u1/2, 2u plus 1. And now I can expand, I can open the bracket, and I'll get something that I can finally integrate. So u 5/2 minus 2u 3/2 plus u 1/2. Questions? Fine. Now it's easy. Almost done. You notice that all the 2's cancel, actually. So I have 1 plus x squared 7/2 over 7 minus 2/5 and I'm done. So this problem is more complicated, as I said, and it requires 2 steps. As usual, I identified the composite function and figured out its differential. I also have something remaining inside the integral, and that I have to express again in terms of u by using the definition usually. Somehow you can modify, you can use the information in the definition to express what is left in terms of the new variable. Okay? Very good. So now this was all indefinite integrals. Very similar theorems hold for definite integrals. But there are subtleties, okay? So I will formulate the problem. So if I have a composite function here and the derivative present inside the integral, I can rewrite it in terms of the new variable u in the following way. F of u du, just like before. But now the thing is that I have to deal with the limits of integration, right? So x changes from a to b. But now I have to know the range where u changes, okay? And u is given by g of x. So the lower limit becomes g of a, and the upper limit becomes g of b. Okay, so the limits of integration change according to our change of variables. And this is very important to remember when you evaluate definite integrals by the method of substitution. Let me show you an example. So let's consider an integral from 0 to 2. 3x plus 1 dx. So first the usual stuff. We have a composite function. It's linear. Its derivative is linear, so we have it here. So we can, with confidence, write u is this, du is 3 dx. Okay? So this becomes square root of u. Du over 3 Okay. All I need to do is to figure out the limits of integration. So when x equals 0, my lower limit, what is u? I have to substitute here, so I have 3 times 0 plus 1 is 1. When x is equal to 2, I substitute again in a definition of u. U is 3 times 2, sorry. 3 times 2 plus 1 is 6. And no, it's not. 7. These are my new limits, and this is what I put here. Okay, when I integrate in terms of u, it has to have its own limits of integration. Very important. If you leave this on, that would be wrong. And now it's very easy to finish. So that's the answer. Question?
When taking into consideration only the final answer, is it okay if we don't find the new limits of integration, just leave it, and then when we substitute x back into the function of u, then we just take it with the limits of x?
Yes, you can do that. So you can first find the antiderivative by using these rules, and then use the new, then you use the old limits. However, I find this method a lot easier. Okay. And less confusing. Okay. Another example. So let's consider the following integral from 1 to 2 dx 1 minus 2x squared. Okay, so a definite integral, u will take it to be 1 minus 2x, and u is minus 2 dx. So without the limits, I have u squared here, and dx is minus 1/2 du. Now I'm going to worry about the limits. X equals 1, u is 1 minus 2 is minus 1, and x equals 2, u is 1 minus 4 is minus 3. So I go from minus 1 to minus 3. Okay, so this is something that I can evaluate. Okay. It's all in terms of u, and it has the correct limits. Now, just technical details. If you notice, I'm integrating from right to left here. Can you see that? I go from minus 1 to minus 3. I don't want to do that. And conveniently, I have a minus sign here. So I can kill two birds with one stone. I get rid of the minus sign and switch my integration such that it goes from left to right. And now I just go through the motions. I go through the algebra quickly. You can check it later. Okay, question?
Why did you switch the -1 and -2?
I didn't have to, but I'm usually uncomfortable going from right to left, right? Minus 3, minus 1. I go from minus 1 to minus 3. So I flipped them, and I got rid of the minus sign.
Oh, okay.
That's all. I didn't have to do that, actually. Okay. Now, the fun part. There are some interesting rules of differentiation that are based on symmetry. Okay. So I want to first define two types of functions, even and odd. So suppose f is continuous on an interval from minus a to a. If f is even, then the integral from minus a to a f of x dx can be simplified to be an integral, 2 times integral from 0 to a f of x dx. And if f is odd, then the following rule holds. An integral from minus a to a f of x dx is equal to 0. Okay? So if you know this rule and if you understand it, it simplifies a lot of integrals. And I'll show you what I'm talking about here. So first we have to remember what is even and what is odd when we talk about functions. So here, f of x is even if f of minus x is the same as f of x. F of x is odd if f of minus x is minus f of x. So what are the conventional examples? An even function, for instance, is a parabola. F equals x squared. When x changes to minus x, the function doesn't care. X squared remains x squared. That's an example. An odd function, a common example is, for instance, x cubed, right? When x becomes minus x, the function acquires a minus sign. For instance, minus 2 cubed is minus 8. Okay? So now we have to look at me. You have to remember the rule. Okay? Even function looks like this, and an odd function looks like this. Okay? So this is something for you to remember and visualize it always. Now, what does the first theorem say? It says that if I take something that looks symmetric, okay? So with respect to the origin, from minus a to a, and I integrate it. This is the same as 2 times just the right half of this integration because of the symmetry. 2 times just this. Okay. The second part of the theorem states the following. If I take a function that looks like this, and I integrate it from minus a to a, what's the answer? 0, because it consists of 2 parts with an opposite sign. And they cancel each other because they have the same area but a different sign. Now, why do we all of a sudden talk about this? It's unrelated to the previous material. Well, the reason is that these are just pictures and they're not a proof. The only way to see this rigorously is to use the rule of substitution. It's a very beautiful proof, which I'm going to demonstrate now. It's very simple. So, proof. Consider the integral from minus a to a f of x dx. And we know that we can rewrite it actually as 2 integrals, from minus a to 0, plus an integral from 0 to a. This is one of the first rules of integration that we learned, right? And now I'm going to take this first integral and make a substitution. I'm going to introduce a new variable u, which is equal to minus x. Okay? So du is minus dx. And I also have to remember it's a definite integral, so when x is minus a, then u is a. And when x is 0, then u is 0. So what becomes of my first integral? I go from a to 0. I have f of minus u, and I have du with a minus sign because of this. Okay, so I applied blindly the rules of substitution to this integral. Okay, where everywhere I see x, I change it to minus u. That's my rule. Questions? Fine. So that's the first one, and the second one is from 0. Oh, sorry, from 0 to a. F of x dx. Now here, I want to flip the limits. So I go from a to 0, and I flip the sign. So I go from 0 to a, f of minus u du, 0 to a, f of x dx. And now, the most confusing part. Look at this definite integral. The answer doesn't depend on u, because it's a number. U, in this case, is a silent variable of integration, and I can replace it with a, b, c, d, or whatever variable I like. So I'm going to replace it back with x. And I lose this connection. Okay? So from now on, it's just a silent variable of integration. And I rewrite it like this. From 0 to a, I simply rewrite it minus x dx, f of x dx. Okay, so now the last bit, I'm going to apply this in the two cases, when f is even and when f is odd. So first, f is even. What does it mean? It means that f of minus x is equal to f of x. Remember, even f of minus x is the same as f of x. Then I get 0 to a f of x dx plus 0a f of x dx, which is exactly 2 f of x dx. 2 is more fun. When f is odd, what is f of minus x?
Negative.
It's negative f of x. So I get negative f of x dx plus the same thing. And what do I get? Minus the same thing, and that's 0. Examples. The examples, the main thing there is to recognize whether a function is even or odd. Oh, by the way, most functions are neither even nor odd, okay? Because when you change x to minus x, you just have a different function. It doesn't have any symmetry properties. But some functions are even, some are odd. And for those, integration in a symmetric region simplifies. So the first example is like this. From minus 3 pi to 3 pi sine x divided by x squared plus 95 minus 6 x to the 8. Okay, so without this new rule, go and integrate it. It's not nice. But so when we look at the integrand, we notice the following thing. If as I change x to minus x, what happens to the denominator? X squared doesn't care, 95 doesn't care, and x to the 8 doesn't care either. So the denominator, when I change x to minus x, stays exactly the same. How about the numerator, sine x? Sine x flips, right? This is a classical odd function. Because sine of minus x is minus sine x. So the whole thing, what does it do when x goes to minus x? The denominator doesn't care. This one flips sine. So the whole thing flips sine. So this is an odd function. So what's the answer? 0. Questions about this? Okay. Another example. From minus 10 to 10, x squared plus 1 dx. What can you say about this function? This one is an even function, right? As you flip x to minus x, it remains the same. So this thing is even. Here, the simplification is not as drastic, but it still helps. So we can replace it as 2 times an integral from 0. And integrals starting at 0 sometimes are easier, because you can easily evaluate things at 0 sometimes. So this is all we can do here. From here, we have to actually do the work and integrate from 0 to 10, as opposed to doing it from minus 10 to 10. See, the minus term, the term at the lower limit disappears. So in this sense, this is nicer than the original integral. So the answer is here 260/3. Questions? Thank you.